Right, so this is May 2018. The questions from May 2018 is at the top there. And I've written some up. So these are the questions. They're just the maths part, not the other bits. And yeah, I will crack on with answering them. So number one says, differentiate the following function, simplifying where possible. Right, so this is a quotient, which means it's a fraction, with functions of x on the top and functions of x on the bottom. Okay. If you remember the quotient rule, you would remember that if y is u over v, y dashed v, u dashed minus u, v dashed all over v squared. Okay, so our y is x cubed sine x divided by e to the x. So that means our u is x cubed sine x and our v is e to the x. Right, now u is actually a product, so we need the product rule then as well. So for the product rule, I'll write it over here. If you've got y is u times v, y dashed first times the derivative of the second plus second times the derivative of the first. Okay, we've got a sign there. Sine differentiates to cosine. Okay, so it's first times the derivative of the second. Derivative of sine is cosine plus the second, which is sine x, times the derivative of the first. Well, the first is x cubed, so that's 3x squared. And v dashed is e to the power x, because e to the x is the only function that it's its own derivative. So when we substitute in, it does say simplify where possible. So y is v, u dashed, minus u times v dashed, all divided by v squared, which is e to the 2x. So now we've got to simplify the e's to the x's. So they divide from the top, and then the 2x becomes 1x on the bottom. So we have that's y dashed, not y. Y dashed is, I suppose if we're simplifying, the top terms, they all divide by x squared, x cos x plus 3 minus x sine x, all divided by e to the power x. It's an e. Okay. So I'll show you what I've done with these sine x's. Sine x there, sine x there. This is 3x squared, which is there with that. And then this is minus x cubed, which is this with this. Okay, there's lots of ways of simplifying it, but I'm happy with that. Right, B, find and classify the stationary points of the function y equals x cubed minus 6x squared minus 15x plus 1. I'm just going to shut the door. Okay. So the first thing to notice here is that at a stationary point, which I'll write dy by dx equals 0. So therefore 3x squared minus 12x minus 15 is 0. Then I observe that all these terms will divide by 3. X squared minus 4x minus 5 is 0. And then this will factorise. So x minus 5, x plus 1 is 0. So we've got x is 5 or x is minus 1. Okay. Next thing to do, look at d2y by dx squared. And it's this one with the differentiate, not that one. Some people do this one. Don't do that one, it's this one. D2y by dx squared, 6x minus 12. Then we can say d2y by dx squared at x equals 5. 6 times 5 minus 12, which is 30 minus 12, which is 18. So therefore it's a minimum, because if you remember d2y by dx squared, if it's greater than 0, it's a minimum, which is in this case less than 0, it's maximum. And then we do look at the second value of x, d2y by dx squared, evaluated at x is minus 1. So that's going to be 6 times minus 1 minus 12, which is minus 18, was greater than 0, less than 0, therefore it's a maximum. Okay, and then so we've classified we've got the x coordinates there and there. We've classified them as min and max. Because it says the stationary points, we need the y coordinates as well. So we can say x is 5, y is 5 cubed, minus 6 times 5 squared, minus 15 times 5, plus 1, 125, minus 150, minus 75, plus 1. Well, so that's 125 minus 225, so it's minus 100, plus 1 is minus 99. And then the other one that we need is x is minus 1. Y is minus 1 cubed, minus 6 times minus 1 squared, minus 15 times minus 1, plus 1. That's minus 1, minus 6, plus 15, plus 1. And that's going to be minus 7, plus 15 is 8, plus 1 is 9. So, summarise, our maximum is when x is minus 1 and y is plus 9. I'll do those, put all those together. Look, x is minus 1, y equals 9, and x is minus 1 is a maximum. So I get all those answers from. And then the minimum, we've got x is 5 is a minimum, and when x is 5, y is minus 99. So the minimum is x5, y minus 99. Okay, part C. Derive the first 4 non-trivial terms of the Maclaurin series approximation for the function f of x equals e to the minus x minus 2 about the value x is 0. Right, the Maclaurin expansion about x is 0. Sorry, already. F of x is approximately equals to f of 0. Let's put exactly equals to for now. And when we actually, f of 0, when we actually work out our first 4 non-trivial, that's when it becomes an approximation. X squared over 2 factorial, f double dash to 0, x cubed over 3 factorial, f double dash to 0, etc, etc. Okay, we can go as far as we like. Actually, e to the minus x is always positive, and when we differentiate it, we'll get pluses or minus of e to the minus x. So these will be the 4 terms, so we're okay. So f of x, e to the minus x minus 2. F of 0 is e to the 0 minus 2, 1 minus 2, which is minus 1. F dashed of x is minus e to the minus x. F dashed of 0 is minus e to the 0, which equals minus 1. F double dashed of x is plus e to the minus x. f double dashed of naught is e to the naught, which is plus 1. And one more, because we need 4. F triple dashed of x minus e to the minus x. Triple dashed of naught is minus e to the naught, which is minus 1. So now we can say f of x is approximately equals to f of naught minus 1 plus x times f dashed of naught minus 1 plus x squared. 2 factorial is 2, and f double dashed of naught is 1. X cubed over 3 factorial, which is 6. F treble dashed of naught, which is minus 1. So this is e to the minus x minus 2 is approximately equals to minus 1 minus x plus x squared over 2 minus x cubed over 6, etc., etc. Okay, part D. Find the equation of the plane which is tangent to the surface z equals 2x squared plus y squared minus 3 at the point 1, 2, 3. And what is the normal to the plane at 1, 2, 3? So for this, we start by saying it's z minus 3. So it's dz by dx, evaluated at the x coordinate, which is 1. That's the x coordinate, the y, and the z. And then that's times x minus the x coordinate, plus dz by dy, evaluated at y equals 2, and then times y minus 2. Right, let's do this. dz by dx is 4x. So dz by dx, evaluated at x equals 1, is 4. dz by dy is 2y. So dz by dy, evaluated at y equals 2. 2 times 2, which is 4. So to get this dz by dx, you differentiate this. So it's 4x, and then substitute 1 from there to get 4. To get dz by dy, you differentiate with respect to y. So it's 2y. Then you put y is 2. 2 times 2 is 4. So therefore we've got z minus 3, 4, x minus 1, plus 4, y minus 2. These are not always going to be the same. That was a bit of a coincidence. So therefore we've got z is 4x minus 4 plus 4y minus 8, and add the 3 from the other side. So z is 4x plus 4y. I've got minus 12 plus 3 minus 9. That's the plane. Okay, so that's it there. Right, so for the normal, you've got to collect the x's and the y's and the z onto one side. So that you subtract from each side. That you add to each side. So that's 9. Then you can say the normal is the coefficients of the x, y and z. So it's 4, 4, minus 1. E. If y is 3x plus 1 to the power x, find dy by dx. Right, so to do this, first of all we take logs of each side. And then using the rules of logs, bring that power down, the x can come down as a multiple. And then we differentiate each side, 1 over y, dy by dx. So if it's log of something, it's 1 over the something. Now the something is a function of x. We don't know what it is, but it is a function of x. So we multiply by dy by dx, the derivative of the bracket with respect to x. The right-hand side is a product. So we have to do first. Oh, come back. What's happening? What's happening? There. Nope. 2018. There. That's it. First times the derivative of the second So it's x, 1 over 3x times the derivative of 3x plus 1. So it's x is first, the derivative of the second. So it's log of something, so it's 1 over the something times the derivative of the something with respect to x, plus second times the derivative of the first. Well, x differentiates to be 1. So we can say 1 over y dy by dx. It's 3x over 3x plus 1 plus ln 3x. So dy by dx is y times all this, multiply both sides by y, and just rewrite the y, 3x plus 1 to the power x, 3x plus 1 plus ln 3x plus 1. Right, number 2, integration. The integral from 0 to 2, 1 over x plus 3 dx. That's ln x plus 3, 2 and 0. So it's ln 2 plus 3 is 5 minus ln 0 plus 3 is 3. So it's ln of 5/3. That's part 1. A2. Okay, for this next one, if you remember, if you've got a function in the denominator and its derivative on the top, plus or minus a constant, as a multiple, not plus or minus a constant, with a multiplier constant, and you integrate that with respect to x, it's going to be the constant times ln f of x plus c. Okay, so because we've almost got that here, now I spotted that because this is x to the 6 and this is x to the 5, and this differentiates to 0. So this top is almost the derivative of the bottom. If you differentiate the bottom, you get 6x to the power 5, and what we've actually got is 3x to the power 5 on the top. So this is actually the integral of a half of 6x to the power 5 over x to the 6 plus 3 dx. And it goes from 0 to 3. Okay, so if you look, our k is a half, because we've got the for f dashed, 6x5, f, x to the 6 plus 3. So this is going to be a half ln x6 plus 3, 3 and 0. 3 to the power 6, that's 9 times 9 times 9. So it's a half ln 81 times 9, 729, plus 3, 782, minus a half ln of just 3. Okay, so that's going to be a half ln 782 over 3. It's 2, remainder 1, 6. Why doesn't that even... Oh, well... Just let me check something. 9 times 9 is 81, times 9 again, 9. 9 8 is 72, plus 3. 32, not 82. Sorry, 732. I knew it should divide by 3 exactly. 732. Let's do 7, 3, 2 divided by 3. 2 remainder 1, 4 remainder 1, 4. A half ln 244. You can spread it out more than that. Right, B. Partial fractions. So we've got 12. That means we need to factorise the denominator. Two numbers that multiply to make 8 and add to give minus 6, minus 4 and minus 2. X minus 4, x minus 2. So I'm going to say it's A over x minus 4, B over x x minus 2. And then if we multiply both sides by x minus 4 times x minus 2, we'll get that 12 is a times x minus 2 plus b times x minus 4. So to work out the b, if we start by substituting x is 2, we get 12 a times nothing plus b times 2 minus 4. So therefore minus 2b is 12, so b is minus 6. Then if we put x is 4, we have 12 a times 4 minus 2 plus b times nothing. So therefore 2a equals 12. I'm thinking on there. So therefore a is 6. So we can say the integral of 12 over x squared minus 6x plus 8 dx is now the integral of 6 over x minus 4 minus 6 over x minus 2. Just doing a quick check in my head. Yep, dx. So it's 6 ln x minus 4 minus 6 ln x minus 2. And for the constant, I'm going to put ln c, because I'll combine them all into a single ln. You can put just plus c if you want, but you'll see this in maths books as well. So this is 6 ln x minus 4 over x minus 2, and then the c can multiply in there. Or if you don't do the c like that, so if you don't want that c there, you just put plus c over that side, plus c, but I'll put it in there. Okay, part C. Use an appropriate technique to evaluate the integral of x squared ln x dx. So we've got L and A log and an algebra. If you remember, this is going to be integration by parts. Integration by parts. And we've got an L and an A. So the L is the U and the V dashed is the A. Integration by parts is the integral of U V dashed dx is UV, and it's the integral of V U dashed dx. But it's not necessarily, as in this example, that the first one is the U, because we've got an L. Ln has to be the U. More technically, the U has to be the function that when you differentiate it becomes less complicated over here. And because ln differentiates to 1 over x, that's going to simplify the V. So that's the thought there. So we've got U is ln x, V dashed is x squared, U dashed 1 over x, V x cubed over 3. Let's add 1 to the power divided by the new power. So this is going to be U times V, we'll put the V first, x cubed over 3 ln x, minus the integral of V times U dashed dx. So it's x cubed over 3 ln x minus the integral of x squared over 3 dx. So it's x cubed over 3 ln x minus, add 1 to the power, divide by the new power, which is 3, but with a 3 that's there already, it becomes 3 times 3, which is 9, plus c. Right, D. Find the area bounded by the curves y equals 2x and y equals x to the power 3 over 2. Okay, so what we're going to do first of all is find out where these two curves intersect each other. So we can say first of all, x to the 3 over 2 equals 2x. This is for the points of intersection. I'm not feeling the urge to square each side. Is that going to be helpful? I won't. X cubed over 2 minus 2x is naught. Factorise x times x to the half minus 2 is naught. So therefore x is naught, or x to the half is 2, which implies that we'll square each side here. X is 4. Okay, I'm just having a quick check. Yes, they would work. So, if you remember, the integral gives us the area between the x curve, between the x-axis and the curve. And these are going to be our, these are going to be our x-coordinates here. So we need the integral from 0 to 4, x to the power 3 over 2 dx. So we add 1 to the power, divide by the new power in 4 and 0. So it's x to the power, it's 4 to the power 2.5 divided by 2.5 minus 0. And I'll get my calculator for that one. 4 to the power 2.5, 32. 32 over 2.5 divided by 2.5. Let's see what that is. 12.8. Okay, and then we do the integral between 0 and 4 of 2x dx. Add 1 to the power, divide by the new power, cancels out that 2, because we've got a 2 there, and they would cancel between 4 and 0. So it's going to be 16 minus 0, which is 16. Okay, so the area bounded between the two. Trying to think what this looks like. You can have a look at the pictures on Google. I won't go over it now. But do the upper one. Take away 12.8, 3.2. Okay, differential equations. Part B is over there, so I'll do part A here. Find the solution of the first order differential equation given by that. The first thing we've got to do is observe that we've got a coefficient of dy by dx, and that's got to be 1. So we need to divide everything by x squared. So we can say it's dy by dx plus, and that will cancel with that, y over x equals 2 over x squared. Then you find the integrating factor. That's the exponential of the integral, and it's the function of x that multiplies the y here. So it's 1 over x there, dx. So it's the exponential of ln x, which is just x. So then you multiply the whole of the differential equation by the integrating factor, which in this case is x. So we've got x dy by dx plus x times y divided by x equals x times 2 over x squared. They cancel, and that cancels with that to make it 1. Now the left hand side, now if you're brave you can go straight to write this down, which I probably would in an exam, but you know, if you write it this way you've got a way to check. See, this is a product, and if you differentiate this product you should get this pair here. So look, first times the derivative of the second is there, plus second times the derivative of the first is there. But you can, once you've got that there, you can, it's always going to be d by dx of integrating factor times y by the way that it's made out. Anyway, it's up to you what you do there. xy, integrate both sides with respect to x. xy is 2 ln x plus c. What's it say? X equals 1, y equals 0. So we're going to work out what the C is now. I just wrote that down. This here comes from the question. X equals 1, y equals 0. So 0 on that side. 2 ln 1, well that's 0 as well, plus C. So C is 0. So we've got x times y is 2 ln x. So y is 2 ln x divided by x. Okay, and the next one. Solve the differential equation. Let's check I've copied that across right. Yes, I have. So we start with the complementary function, which is we solve the equation with a 0 here. Because like whatever happens, if you've got something that you put into here and it comes up as 0, it's going to work. And that's the idea behind that there. And that they are e to the kx. We assume that it's actually a e to the kx. And sometimes, quite often, there's two values. So we've got to find the k1 and the k2. Well, the k1 and k2 are the solutions of k squared minus 3k minus 4 is 0. So this is k minus 4, k plus 1 is 0. Because if we factorise this, k squared minus 3k minus 4 is 0. Minus 4 times 1 is minus 4. Minus 4k plus 1k is minus 3k. And the k squared, you can see that that's there. So what k is 4, or k is minus 1. So the complementary function is a e to the minus x plus b e to the 4x. And then we look for what's called the particular integral. And then what we try there, when you've got sines or cosines or a mixture on the left, whichever, even if you've only got one sine or just cosine, you always try y equals a. So, oh no, I'm not going to use a because I've already used a up there. C sine x plus d cos x. And the reasons why you need to use cos x, even though there isn't a cos x there, is because when you differentiate cos x and substitute in there, you get coses. You get sines. So you need to be able to combine them all together. So you can't miss them out. Right, so y is c sine x plus d cos x. So we're going to substitute this into the left-hand side. We've got that one, we need that one and that one. Combine them all together with these multiples and set them equals to 1 sine x plus no cos x. So y dashed, sine goes to cosine, cosine goes to minus sine, and then the second derivative, cosine goes to minus sine, sine goes to cosine. And then we want d2y by dx squared. What I'm going to do is I'm going to put the sine x's on the top, the cos x's down here. So d2y by dx squared, that's minus c sine x minus d cos x. I've done that one. And then y dashed, we want minus 3 y dashes. So we've got minus 3c in the cos x, which is that one there, plus 3d for the sine x. And then for the y's, we need minus 4 of them. So we'll multiply that by minus 4. So we've got minus 4c in the sines, minus 4d in the cosines. That's those. So I've done that one, I've done that one. And then I want sine x. So they've got to be equals to 1. And they've got to be equals to 0. So we've got 3d minus 5c is 1. That's from equation 1. And equation 2, minus 5d minus 3c is 0. Okay. So if I make looking at this here, if I multiply this one by 5 and this one by 3, then I add the two together, we'll get rid of the d's, we'll be able to work out the c, and then go on and work out the rest. So that was equation 1. That's equation 2. So 1 times 5 gives us 15d minus 25c is 5. 2 times 3 gives us minus 15d minus 9d is 0. Add them together, they cancel like we expected. Minus 34d is 5. So d is 5 over minus 34. And then we've got, substitute for d in 1. 3 times d, which is here. 3 times d, so it's 3 times this. 3 times 5 over minus 34. Minus 5c is 1. 5 times 34. Just doing all the fractions. You could probably do this on your calculator. 5 4s are 20, 5 3s are 15, 170. Add 5c to each side. Take 1 from each side. So we've got 15 over minus 34. Take away 34 over 34 equals 5c. Didn't need that over there. Was there? Unusual numbers. I do seem to remember this coming up in the exam there. 15 minus 15 minus 34 is minus 60, minus 49. C is minus 49. Because what I've done there is I've put that minus up there. Minus 15 minus 34 minus 49. And then divide by 5. But it's already divided by 34. 34 times 5, 150, 170. So we need to summarise this really. I'm going to write here answer, which should be at the bottom, but I'll put it at the top. That's the particular, so the particular integral, y particular integral is c sine x, which is, where was my c, minus 49 over 170. Sin x plus d cos x and d minus 5 over 34 cos x. Actually, so I'm just going to do 49. I don't think that cancels. 49, 170. I don't think it did. So the answer, y is a e to the minus x, b e to the 4x, minus 49 over 170 sin x, minus 5 over 34 cos x. Yeah, that seems unusual. I'm going to check that. Yeah. Anyway, the method's right. Just the arithmetic seems a bit unusual. I'm pretty certain. I remember 34s last year, so or the year before. So there we go. We'll stop there.